without much further ado, I'm going to start my own presentation about using evolutionary algorithms for server hardening via the moving target defense technique. I'm going to share my screen. I hope I don't break anything. I'm not going to share computer sound because I'm going to speak. So here we go. Everything is okay? Can you hear me? Say yes if you do.
Yes, yes.
Yes.
Okay, that's perfect. So this is a research we did in the University of Granada with Ernesto Serrano and Pedro Castillo, who is around here. Ernesto Serrano, I don't think he's around here, but he was a master's student. And actually, while he was doing this, he was a high school professor in the beautiful island of El Hierro, which is down south in front of the African coast. But this is a very interesting work, I think, which is basically about what is called the moving target defense. So this is Target. You see the Target supermarket chain in the US. We are going to talk about that. The basic idea is that we want to defend our servers, we want to defend our services which are on the internet by making them a moving target. The thing is that whenever somebody's attacking a series of hosts, one of the first things they do is to kind of profile every kind of server. So they kind of try to get like a signature of every server by finding out not only the kind of service they are doing, but also other features or metadata from the server. Like for instance, what kind of server they're running, what's the response time and everything. By making them a moving target, you will not allow them to get like a hang or like a hook on a particular server, because every time they connect to a server, it will present a different face or a different kind of response. The kind of measures you can take on the packets that the come and go in the network are going to be totally different every time. The basic idea then is that you create a service, you configure that server in such a way that after a random amount of time, you totally change the configuration without, of course, compromising the performance, which is always important. So that's what we are going to do. We're going to create different service configuration. Every service that is facing the internet, like web servers or SSH servers or a whole virtual machine that is serving on the internet or image or whatever, has a particular configuration with many different facets that you can change. So that's what we're going to do. We're going to create different service or server configurations. We are going to change them frequently, right? We're going to focus on web server configuration. Why? There are several reasons. One is because it's relatively easy to assess the security of a server configuration. The second reason is also that we are very heavily inspired by a paper that was published in Gecko in 2014, which was also focused on server configuration. Also, a server is out there on the internet. It's one of the most important kind of services that you have. But the thing is that instead of using Apache, we're going to use a different server, which is nginx, which is quite popular. It's probably one of the most popular services, web service that we know. It's not only used for web service, it's also used as an inverse proxy. It's also used as a API gateway for many other things. It was originally created in Russia, and now it's one of the most popular out there, even I think even more popular than Apache. So the thing is that we are going to use an evolutionary algorithm that finds secure configuration. And those secure configurations, we need to create a lot of them. We need to generate a lot of them. Why? Because if we want to present a moving target to the internet, one of the things we need to do is to change them often. So not only we have to create a configuration that's secure by itself, but we also need to create lots of them. That's one of the main things we need to do, right? So the first thing we need to do in an evolutionary algorithm is to generate the configuration. So we need a way from data structure that we do custom, we need to generate a configuration using nginx. Then we need to examine the vulnerabilities of a real site, because generally a configuration is not something that you just put there and it's totally static. It has nothing to do with what's behind it. But we have to take into account what's really behind that. You can have a very, very safe configuration, but if you have something behind that's unsafe and it's not made safer by the configuration, it's going to be bad. So we need to work with a real site, and then we need to evolve it, right? Let's see how we're going to do the first part. The first part is that we are going to use nginx. Nginx has around 700 different parameters, as almost every other service on the internet right now is secure by default. So that means that if you don't say anything about a particular value of a particular parameter, the default you are going to get is going to be well, safe. Probably not the safest thing in the world, but safe enough. But we're going to choose 15 of them. Those 15 parameters are, some of them are server values and some of them are related to the headers. Every time a server, an HTTP server sends a response, it first sends a header, and that header contains things like usually there are instructions for the browser, like you shouldn't do this, you can't do that. This is the type of content that I'm serving, and so forth. Also, these values are quite related to the values that were used by John, the person that did this original paper in 2014. And then we are going to use something which is called SAP. SAP is Zero Attack Proxy. Was created by an organization which is called OWASP. What SAP does is it gets into a server. It spiders the whole server. It spiders all the services that are there, and then it starts to probe every vulnerability that's there. And at the end, it gives you a score, like saying, if you do this, it's got this particular vulnerability. This is a medium or a high or a low level vulnerability, or this is just information. So what we are going to get from every configuration we are going to test is a number of alerts, the number of things that are wrong with the configuration. This is going to be a cost. We're not going to work with fitness because we want to make things as safe as possible. So that means that we are going to evolve so that we have as few alerts as possible. Few alerts is going to mean few vulnerabilities. It's going to be almost impossible to get to zero vulnerabilities, but we'll try to get as close as possible to zero. Anyways, we are going to use two different web services. As I said, configuration is usually meaningless without something that's behind it. One of them is a simple static website with 4 pages. One of them is a form, and the others are just static web pages. Unsurprisingly, you can create a static web page that's unsafe, because it's for instance, it could be vulnerable to cross-site scripting, things like that. And the other thing is a Jewish shop. The thing with the Jewish shop is it's a container that was created also by a WASP, and it's something that was created unsafe by default. So it's the kind of case study that's used precisely to do this kind of thing. So it's something that we know it's unsafe. So even if it's unsafe, we will try to put in front of it something that's as safe as possible using our evolutionary configuration created with nginx, right? What are we going to do with this evolutionary algorithm? We are going to try and minimize the number of alerts. We're going to try and have as few alerts as possible. So we are going to evaluate, create a configuration. We evaluate it using SAP, and we will try to make that the fitness, and we will try to minimize the number of alerts. So the cost is going to be minimized. And we use something, we use Docker Compose. We actually have 3 containers. One of them contains SAP, which is actually a proxy, so that that proxy records every request and every response. It examines the request, examines the response, checks if there's something wrong with the response. If there's something wrong with the response, it raises an alert. And we also use a homebrew evolutionary algorithm. Why do we do this? Well, because it was easier to do it that way, because we had to put it inside a container and everything. So eventually we found out it was the best thing to do. So we could have used any other evolutionary algorithm library out there. It was written in Python, and everything, of course, is open source. So if you check out the GitHub repository for this, everything is going to be there: the paper, the data, all the experiments, and also all the code for this. I can give you the GitHub address after this. Anyway, if you look up in the GitHub and check, look for the title of the paper, you will find it out. We do open science, so that's something we always do. So you can always check out the papers we are working in. For instance, right now we are working on very interesting papers for PPSA, and you are probably doing the same now. Anyway, these are the results. One of the things we wanted to investigate was a result of different types of crossover, because it was rather something like an initial exploration of the thing. So we were trying to do different things with evolutionary algorithm. As I said, it was homebrew, so we really need to check how it was working. We used two different kind of mutations. One of them was called 1, and this one mutation, what it was doing was changing the value of a particular parameter by just 1. And the other one was called random. This random was totally destroying the value of a particular parameter, and I was substituting it by a different value, right? So we represent that with a little dot, random with a triangle. And what you can see here is that it's pretty much the same. It doesn't really matter if we use one of the other, it's going to work out in the end. We did it for different population size, because we were also interested if there was going to be some influence on the population size or on the results. What we see here is that the bigger the population, we get kind of better results. But you see that all the results are in two different levels. One of them has, if I remember correctly, was 12 alerts. The other one had like 3 alerts, and it didn't change like a lot. So it wasn't really like a big influence. Maybe we also check out the crossover, but the crossover was also pretty much the same. So if we use 1-point crossover, results were kind of a little bit worse. If we use 2-point crossover, it was a little bit better, but not by far. We also put some more information here. One of the things that we see is that the transparency of the figure is related to the number of days that this took. This really took a long time. Every time we were checking a configuration, it took, in some cases, close to 1 minute. So it was really, really heavy to do that. Of course, if we use a population that's smaller, we have less evaluations. And this is clear, which means that it's not taking as much as 4% of a day, which is 4% of a day is kind of 24 hours. Yeah, it's kind of 1 hour. In this case, it was 2 hours or even more, right? And the other information that we are presenting here is one that we were really interested in. It was the number of copies of configuration with the best value in the last generation. So the idea was to, once you have done the evolution for a number of generations, you see what's in there, you see what's in the population, and you check if there are several individuals with the best value. And you can also see here that in the case that we get the kind of worse, it's not really bad, but kind of worse configuration, we got many copies with that value. In the case we had the best configuration with less alerts, there were few of them, so maybe there were like 1 or 2 of them. This doesn't mean that they are insecure. What it really means is that, okay, there is something to it, because there are several kinds of alerts. Some of them are informational, which means something like, okay, check this out. It's not going to be, it needn't be bad, and you need to check this out, right? So that's something we're really looking at. And then with the same for the static web. In the case of static web, there is basically almost always the same number of alerts. Take into account that this is a very rough landscape. It means that whenever you change a single value, it can increase the number of vulnerabilities by a lot. So very few of them were actually able to find this lower level of vulnerabilities. And it was only when we were using random mutation, and it was only when we were using the one-point crossover. This probably is just by chance, but it also reveals that trying to find out the vulnerability, I mean, how vulnerable a particular configuration is not so easy. It's something that you could could take like lightly, something that you should really consider. Then the thing, as I said, which is also very important, we're also looking at is how many copies we have. So how many configurations are we producing using the evolutionary algorithm that we can really use for a moving target defense? This is a plot that we did with 16 individuals in the population, 32 individuals in the population, also 64 individuals in the population, and also for the static and the Jewish shop. The static website is kind of easier, so it's kind of easier to make it secure because it's a static. The Jewish shop, as I said, is quite insecure by default, so you really need to push it very hard and to know very knowledgeable about the nginx configuration to make it as safe as possible. And what you see here is that it's relatively easy to find something that had the maximum or the minimum vulnerabilities for the static website. It's not that easy for the Jewish shop. In some cases, you're going to have something that only has well, this is probably like 1 or 2 individuals in the population. This is something really that we should look at. So the number of copies that we have in the population, because it's going to allow us to really make this moving target defense by creating configuration. Another thing that's important is how long does it take? And this is the percentage of a day, so the number of days. 0.10 days would be 2.4 hours. So if we are using the Jewish shop, it's going to take really a long time. It's going to take almost 2 hours to evaluate, and take into account that we are doing very few evaluations. So we are doing our generations are only like 32 individuals or 16, I don't remember exactly. But no, it's 16, 32 or 64. But in any case, it's going to be take a long time. This is something that is really a challenge, and it's going to be something that we need to improve in the future. So the problem is that eventually it takes a long time, but we can get enough secure nginx configuration using evolutionary algorithm, and that's good. That's pretty good. That's what we were looking for. Of course, it's going to depend on what we choose to make this kind of configuration secure, but it's going to depend on how we measure the fitness. But in any case, we're going to get a few of them. It's going to take some time, but take into account that you don't need to change the configuration every few minutes. So maybe you could change the configuration every 2 or 3 hours. I mean, a random amount of time. It's going to be quite enough. There is some room for improvement, of course, but we're looking for a moving target, and we can say that evolutionary algorithms not only move the target, they rock the target. And that's it. Thank you very much. I'm going to try and stop sharing, but it doesn't allow me. So maybe Pedro or Juan can do it for me. I'm just clicking on stop sharing, and it doesn't. So can someone please do it for me?
I don't know.
Oh. I'm trying, GJ, but yeah, there is something weird.
Okay, I just can't do it. You know, it's.
Yeah, I did it.
Okay, thank you very much.
I did it.
So, Questions?
I have a very simple question, not
Okay, thank
related
you.
with the IA actually, but related with the transition. Since you are changing the configuration of your service, have
Yeah.
you? I mean, there is a smooth transition between services, or I mean,
That's a good
between
one.
the same service with different different parameters, or what does that imply?
I didn't really give that a lot of thought, nothing at all. Yeah. So in fact, you have to take down the service for maybe a few seconds and then bring it up again. That if I mean, for the kind of configuration we were using, it takes all of maybe a couple of seconds. So when the service is down. So I think that what we will be doing in a production environment will be something like have several servers at the same time. So we would probably set up a twin server that will start to serve to make the same service and then bring it down, right? And then we will bring it up again. So that would be something we would do. Anyway, I mean, takes a few seconds. It also depends on how you do it. If you do it using Docker containers, it's going to be relatively fast. I don't know if that answers your question.
Yeah, definitely.
Okay,
Yeah.
thank you very much. So there's another question by Bill Landon. He says that there is some scope for parallel. As a matter of fact, there is, but the problem is that for the particular configuration that we were using, which was using some Docker containers, we were using some specific ports in the host. So that meant that we should have to configure it so that we were using different ports for different things. So also setting, we were using Docker Compose, which is not the best way to do that. If we were using something more advanced like Kubernetes, probably we could do it a bit faster. I don't really think the problem can be solved by parallelizing it. Of course, you can do several evaluations at the same time, but I'm not sure that we are doing the evaluation in the best possible way. So at the end of the day, what SAP is doing is using some heuristics on the response that you get from the server. Maybe those heuristics could be done in a different way, or doing directly on the configuration itself without needing to fire up a server and everything. So, I mean, it's kind of tricky. So the implementation is tricky, and if there was no other way out, we will eventually do it, but we will probably explore some other way of doing it. So thank you very much, Bill. It's a very good question. Then Douglas Diaz is asking, did you use cloud compute nodes or local physical computers to run the experiment? It's also a very good question. We're using Docker Compose. As you know, Docker Compose is not exactly a production tool. It's more like a development tool. Theoretically, you could deploy it to any node on the web, but in this case, the three containers that we were using were in the same computing node. We did all the experiments in this case, we were doing it on the cloud. If I remember correctly, we were using Azure, and Azure cost, all of it costed like $13 or something like that. So, but we were not deploying the containers, everything independently. So they were all of the three containers were deployed to a single node, a single instance in Azure or Amazon, I don't remember exactly. And then the whole thing was like not a lot. It was like $13 or so. You can use the cloud, but the problem is that if you run the containers in different nodes, latency is going to be higher, so it's going to take even longer. So everything is prepared to run on the cloud. And in fact, it was from the get-go done like that. One thing we want to do is in the future, maybe not run it on the cloud, but running using some free service, actually using some continuous integration service like Travis or GitHub Action or something like that. But it's not, I mean, I teach cloud computing, so we were using the cloud as if we were using a laptop computer. And if, in fact, to do the tests and everything, they are done in a laptop, and they can be done like that. Thank you very much for your question. So, any other question? No? Okay. So, it's about time for my gym class. So I'm going to close the session. Thank you very much for sticking around. You have the poster session right now, starting in 6 minutes. Please go there. I'm gonna be there in a while. So that's basically it. Thank you very much. Bye-bye. Stay safe and see you next time.